Okay, so far we have talked about, we're talking about the respiratory system, and I told you at the beginning of this chapter that we would be talking about 4 different processes. So far we've talked about pulmonary ventilation, okay, and this is just bringing air in and out of the lungs. The next thing we're going to talk about is pulmonary diffusion, and this is the movement of gases from the lungs into the blood and from the blood into the lungs. Okay, so pulmonary diffusion is gas exchange between the lungs and the blood, and this gas exchange occurs in the pulmonary capillaries, and basically it occurs between the pulmonary capillaries and the alveoli. Okay, and the pulmonary diffusion serves 2 functions. It's to bring oxygen in and to get CO2 out. Okay. So if we trace oxygen as it moves, okay, oxygen originates in our atmosphere. From our atmosphere, it comes into our alveoli. From the alveoli, let's see. Okay, so it starts in the atmosphere. From that, it comes into our lungs. More specifically, it ends up in your alveoli. From the alveoli, that's where we get pulmonary diffusion, and the oxygen will move into the pulmonary capillaries and into the blood. Okay, and then the pulmonary capillaries empty their blood into the pulmonary vein. Okay, and the pulmonary vein brings the blood back to the heart, left atria to left ventricle, and eventually ejects the blood into the aorta, and now the oxygen can go out into the system and get delivered to your tissues and your cells. When we look at CO2, CO2 is going to originate in your cells or in your tissues, okay, and it will leave your cells and your tissues, and it'll end up in your venous blood. Okay, and the venous blood ends up in your vena cava, which enters the right atrium and brings the blood into the heart. Okay, and from there it goes to the right ventricle. From the right ventricle it leaves the heart through the pulmonary artery and ends up in the pulmonary capillaries, which surround the alveoli, and diffusion occurs, and the CO2 ends up in the alveoli, and then we exhale it into the atmosphere. Okay. So pulmonary diffusion is very simply gas exchange between the lungs and the blood. Oxygen moves from the lungs into the blood. And CO2 is going to move from the blood into the lungs, so we can get it out. All right. So if you look at the anatomy, okay, here at the end of your bronchioles we have air sacs called alveoli. Okay, and there are approximately 300 million alveoli in a human's lungs, so they're very, very tiny little air sacs filled with air. And the alveolar membrane is very thin, 1 cell thick. Okay, and surrounding the alveoli is a very dense network of capillaries, and the capillaries have membranes that are also very thin, 1 cell thick. Okay, so it can't get any smaller than 1 cell thick. So together, the respiratory membrane is made up of the capillary membrane, the alveolar membrane, And so the respiratory membrane is 2 cells thick, very, very thin. So together, the alveoli and the capillaries are very well suited for gas diffusion. It's very easy for a gas to move across such a tiny little membrane. And so you can see here, this is here's our capillary, here's your alveoli, here's your membrane, and we've got oxygen moving from the alveoli into the capillary, and we got CO2 moving from the capillary into the alveoli, so then we can get rid of it. We can exhale. Okay, and this oxygen is coming in. So, what is the driving force for this gas movement? Why is oxygen coming in? Why is CO2 going out? Why does it move in the direction that it moves? Okay, why do they move in these directions and not in the reverse direction? Well, it shouldn't surprise you that the driving force for gas exchange is a pressure gradient. Okay, just like blood flow through the heart, gases are going to move due to pressure gradients. So these gases exert pressures that will determine which direction they move. So a pressure of gas would be PO2. Okay? And if we know that gas is moving from the alveoli into the capillary, that must mean that the PO2 in the alveoli is greater than the pressure of oxygen in the capillary. Okay? So the same thing is true with CO2, is that it has a pressure, and if it's moving in this direction, it's moving from the capillary out to the alveoli, that must mean that the pressure of CO2 in the capillary is greater than the pressure of CO2 in the alveoli, and that's what's driving the movement in those directions. So what we're going to talk about now are these pressures of gases, which are called partial pressures. Okay? So I'm going to take a step back and explain to you some really simple concepts. Just be prepared that the first time around it's going to be a little confusing. But once I've gone through this, I'm going to put some numbers to this, and once the numbers are there, I think it's going to start to come together. So basically, let's start with ambient air, which is air in the atmosphere. Okay, and we can measure the pressure in ambient air. Okay, and that is called barometric pressure. So you've probably seen this on the weather report when they talk about a high pressure system coming in or a low pressure system coming in. What they're talking about is barometric pressure, which is also known as total pressure of ambient air or total pressure of atmospheric air. And normal barometric pressure under standard conditions is 760. Okay, millimeters of mercury. Remember, millimeters of mercury is a measurement of pressure. Standard conditions means that you are at sea level, the air is dry, basically zero humidity, and the temperature is 32 degrees Fahrenheit. Okay, so under those conditions, the barometric pressure is 760. Most of the time, these conditions don't exist, but this is just a theoretical number that if you were at sea level with no humidity and it was exactly 32 degrees Fahrenheit, the pressure in the atmosphere would be 760. And then we start from there and we talk about how this pressure would vary under different conditions. But for our example, we're going to assume that the pressure in the air is 760. How do we get this? We measure this with a barometer. So like a thermometer that measures temperature, there's something called a barometric, there's something called a barometer that will tell you what the barometric pressure is at any given time. Now, the atmosphere is made up of a mixture of gases. Usually when we say air, people are thinking oxygen. And yes, there is oxygen in our air, but there's also CO2 in our air, and there's also nitrogen in our air. Okay, so this atmospheric air is made up of a mixture of gases, 3 primary gases, and the total pressure of this atmospheric air under standard conditions is 760 millimeters of mercury. Okay. Now, according to Dalton, the total pressure of this gas mixture is equal to the sum of the individual pressures. Okay, so if the total pressure is 760, and we know that because we measure it, that's telling us that if we add up the pressures of these individual gases, together they are going to equal 760. Okay, so the total pressure of a gas mixture is equal to the sum of the pressures within the mixture. Okay, so if we knew the pressure exerted by each of these gases and added them together, we would get 760. Okay, and I'm going to provide an example of that, a real example of that, which will help here in a minute. All right, so this is something we know. Okay, another thing that we know is that the gases that are in the mixture are exerting pressures that are in proportion to their concentrations in the mixture. Okay, and we also know that the concentrations of the gases in the mixture are constant. Okay, so it doesn't matter where you are on Earth. You could be at sea level, or you could be at the highest altitude on Earth, which would be Mount Everest, and the percentage of oxygen in that air is going to be the same. Okay, so these are things that you need to know. These are constants you need to know. So oxygen is always 20.93% of our air, CO2 is always 0.03%, and nitrogen makes up the bulk of our air at 79.04%. So those are known. All right. So if we can measure the total pressure, and we know that gases exert pressures in proportion to their concentrations, and we know their concentrations, then we can easily calculate their partial pressures in that mixture. So, pressure exerted by an individual gas in the mixture, which we call partial pressure, PO2 is partial pressure of oxygen, then the partial pressure can be calculated by multiplying its concentration, which is known, by the total pressure, which we measure. Okay, let me show you the example here. All right. So here we have our concentrations, which are known. These are always the same, and these are the numbers that I just showed you on the last slide. We can measure total pressure. Okay, so for our example here, we are going to go with standard atmospheric pressure, 760 millimeters of mercury. So we took a barometer and we measured the pressure, and we found that it was 760 millimeters of mercury. And so we know this, we measure this. Now the next thing is, if you're going to, I've told you this before in a previous chapter, that if you're going to do math with percentages, you can't use this value. You need to use the fraction value. And let me show you what I mean by that. Okay, so 79.04% basically means 79.04 out of 100, and if you do the math there, it's 0.7904. Okay, so these are equivalent, but if you're going to do a calculation, you need to use the fraction, not the percent. Okay. Now where you need to be careful is when you are converting CO2, which is 0.03%. Okay. 0.03 out of 100 is 0.0003. Okay. So basically what you're doing is you're moving the decimal point 2 places to the left. When you do this with CO2, in order to move 2 decimal places to the left, you need to add a 0. So make sure that you get that right, because some people get lost with all the zeros. Alright, so the fraction for nitrogen is 0.7904, for oxygen is 0.2093, for CO2 is 0.0003, and now all you do is simply multiply its fractional concentration by the total pressure, and it gives you the partial pressure of that gas. So 0.7904 times 760 is 600.7. And so the partial pressure of nitrogen in this mixture is 600.7 millimeters of mercury. You do the same for oxygen, and you do the same for CO2. Okay, now you know the partial pressures of the 3 gases in the mixture. And as Dalton said, if you add up the partial pressures of the gases in the mixture, you end up with the total pressure of that mixture, which is what we originally measured. Okay? So for this class, I may give you total pressure. I may tell you, all right, I used a barometer, I measured, and it's 755 millimeters of mercury. Tell me the partial pressure of oxygen in that mixture. So you would need to know to multiply that total pressure by the concentration of oxygen, which would be 0.2093. So make sure you do this in the workbook, because I've given you an example of this in the workbook on how to do this. It's really important for you to understand partial pressures, because those are the pressures that determine the pressure gradients that determine which way these gases move. I'm not so concerned about nitrogen, because we're not going to talk about nitrogen movement. So focus on oxygen and CO2. And remember that the sum of the 3 percentages is always going to equal 100. So if you knew the concentration of CO2 and oxygen, you could easily calculate nitrogen, because you could subtract these two from 100. You're going to get the 79.04, which is nitrogen. All right, so I just want to go on a little side right here to talk a little bit about altitude, because at this point some of you guys might be thinking about trying to make sense, because you know that you've all heard that when you go to altitude, exercise is more difficult. And most people think it's because the percentage of oxygen is lower at altitude, but that's not the case. Okay, so the percentage of oxygen in the air is always 20.93%. Okay, just as the percentage of CO2 is 0.03, the percentage of nitrogen is always 79.04. So it doesn't matter if you're at sea level in Miami, Florida, or if you are up at 29,000 feet on Mount Everest, oxygen is always 20.93%. It's a constant. Okay? What does change, however, is the barometric pressure. Okay, so if we're at sea level, the air is dry and it's 32 degrees, we're going to have a barometric pressure of 760. As the elevation changes, the barometric pressure goes down. So as we go to higher elevations, we have lower total pressure. So that when we get up to Mount Everest, instead of a total pressure of 760, we would have a total pressure of 253. So the total pressure of all the gases is much lower at altitude than it is at sea level. And this is what causes the problem, because the PO2 is, to calculate the PO2, you multiply the barometric pressure by the concentration, and remember that the partial pressure of oxygen at sea level is 159.1, okay? But if we go up to Mount Everest, we're still at 20.93%, okay? But the total pressure is 253, so when you multiply 0.2093 times 253, we end up with a much smaller partial pressure. So the partial pressure of oxygen on Mount Everest is much lower, okay? And remember that the driving force for oxygen into the body is the pressure gradient. Okay? And if oxygen is coming into the body, right, it's P1 minus P2. P1 is the higher pressure, and that's going to be PO2. Okay? And so if PO2 is lower, then P1 minus P2 is going to be lower, which means we have a lower gradient, we have a lower driving force to bring oxygen into the body. And that's the problem that we encounter at altitude. It's not that there's a lower percentage of oxygen in the air, it's that the oxygen is exerting a lower pressure, so it's harder to get that oxygen into the body, more of a challenge.